And now Bing ZHANG will tell us about from gammaray bursts to fast radio bursts.
Okay, so good morning, everyone, and it's my pleasure to come here and give this talk and thank the organizing Spatial Remote Repeating for the invitation. So I'm going to talk about two types of cosmological bursts in the two extreme electromagnetic spectrum. One in the high energy end, which is gamma ray burst. The other is the low energy and the fast radio burst, as Vicky just discussed. So the part one of this tale of two bursts is gamma ray bursts. Just a little bit back in the history, in 1967, actually July 2nd, so that was the very first time that human registered the very first gamma ray burst with the Vela telescope. As you all know, this is very completely unexpected. The paper was published 6 years later in 1973. The rumor was that it was not declassified because the data initially was to monitor the compliance of the nuclear test ban treaty. However, according to the first author, Ray Bazadov, he said actually during that many years, they're just trying to figure out whether this is astrophysical or not, because immediately they know it's not nuclear bombs. And so the first, for all these explosions, the bursts, the first step is to ask, are they astrophysical? And the next step is to ask, where are they? Because the error boxes are usually pretty big, so there are so many possibilities, ranging from very close to the Earth and all the way to cosmological distances. And in early years, it's quite clear that GRB's spatial distribution is isotropic. But still, one can create all different possibilities. There was a distance debate, either very close to the solar system or extended halo. It's not working. Extended halo of the Milky Way or all the way to the cosmological distances. And then until 30 years later, and thanks to the great efforts of Beppo Sachs, human for the first time discovered the afterglow of GRBs, pinned down found the X-ray counterpart, optical counterpart, and do we have other pointers? And also measure the redshifts. This is all known history. I want to emphasize that seems like nature likes to communicate with us during the year ending with number 7, from 67 to 97. And the third question is what makes them? And this is a great challenge. And back in mid-90s, there was a review which summarized 128 models for gamma ray bursts, and all crazy, most of them are crazy models. But this is a famous quote by Melvin Ruderman: "The only feature that all but one, and perhaps all of very many proposed models have in common is that they will not be explanations of gamma ray bursts." So they are most should be wrong. And the next question is, are they destructive or non-destructive among those models before the discovery of the afterglow? Then for destructive ones, they're non-repeating, just happen once. For non-destructive ones, they can repeat. And turns out history showed that there was one repeater, which initially known as GRB 790305, was a repeater. And later, we know that it is actually not a traditional GRB. It is in the Large Magellanic Cloud, and it later is called soft gamma repeaters. And their origin are magnetars, old, slowly rotating, highly magnetized neutron stars, which can repeatedly dissipate their magnetic energy. And then, among the others, those are destructive ones. There are still two types, short hard and long soft. And the long bursts were quickly identified as associated with the collapse of massive stars, but short GRBs have been speculated as double neutron star mergers until very, very recently. Again, Nature communicated us in number ended with 7, 2017. This very first association between the gravitational wave event and the short gamma ray burst. I would say this plot, which has been shown many times at this meeting, is the most beautiful plot in astrophysics. It's not the right one. The right one is the artist's conception, but the left one, because these are two great efforts, independent efforts in two communities. One in the high energy gamma ray community, decades of efforts trying to figure out what's the origin of GRBs, and left is the gravitational wave community, which again is decades of efforts trying to detect gravitational waves. But both fields point towards one same source, which is double neutron star mergers. And with the detection of this joint detection, we now closed this picture. I think one can say that the big picture of gamma ray burst is finally solved. So we have this theoretical framework. So we have a central, we have a progenitor. So right now we have, let's see if this works. This is not working either. But so we have two types of progenitor. One is the massive star core collapse, the other compact star mergers, and then somehow form a central engine. The central engine could either be a black hole or a highly spinning magnetar. I'll come back to that later. And then launch a relativistic jet towards us with a Lorentz factor greater than 100, and go through transparency, which is called the photosphere, and then in some distance dissipate the energy and produce gamma rays, and eventually decelerated by the ambient medium and produce the broadband afterglow. The big picture is solved, but there are a lot of open questions remaining in this field, including the progenitor classification, the more detailed classifications, for example, whether black hole neutron star mergers can make short GRBs, the central engine, black hole, and millisecond magnetar, ejecta composition, whether it is fireball or Poynting flux dominated, energy dissipation mechanism, shock versus spectator reconnection, particle acceleration radiation mechanism, synchrotron inverse Compton causal thermal, and finally the afterglow physics. I don't have time to discuss all these, which will be discussed in great detail in the upcoming book of this book from Cambridge University Press. But with the time here, I want to talk about central engine. So in principle, nothing can rule out these two types of central engines. It looks like both possibilities. One is a stellar mass black hole accreting from some torus, either from massive star or the remnant after the merger, or a millisecond, very rapidly rotating neutron star, probably highly magnetized. So the current argument seems to me that both engines seem to work actually in both long and short GRBs. Let's go back to this special event, which has been discussed extensively, especially by Sweep here on Tuesday. A commonly asked question, especially, well, essentially every meeting people will ask, what's the origin of this 1.7 second delay? So one can say we can have central engine. There's an intrinsic central engine delay. There's a delay of launch the jet, say 1 second-ish. Or why is that? Maybe that is related to the formation of the black hole. After 1 second, the black hole starts to form, and then accretion starts. Or delay the dissipation of magnetic fields, and so on and so forth. But to us, this is actually discussed in a paper led by Binbin Zhang, who is sitting here, Nature Communication. So it's very intriguing to us. There are two time scales. One is the delay time scale is 1.7 seconds. The duration of the burst is also 1.8 seconds. Those two numbers are essentially the same. So in this regard, we don't really need to introduce a delay from the central engine, simply because based on the standard gamma ray burst mechanism, the jet takes some time, which is defined by R over gamma squared over C to reach the dissipation radius. And the duration is also defined by that simple formula. So within this picture, it's just a standard gamma ray burst, even though luminosity is lower, which means it's a structure jet we are viewing at a large viewing angle. And there's nothing special within this picture. If we don't introduce an intrinsic delay from the central engine, then the cocoon emission may be much, much weaker because one needs to wait a little bit to make the ejector to expand to a larger distance to make the cocoon emission become significant. So within this picture, we don't need to form a black hole. So in principle, one can have a long-lasting neutron star there. Then the question is, a long-lasting neutron star allowed? Of course, from the gravitational wave data, you cannot rule out, so it's impossible. So the upper, this orange part is the upper limit, and this open white circle is actually the prediction. So there's 1 or 2 orders of magnitude difference. So one can have a long-lasting neutron star emitting gravitational waves, but cannot be detected right now. And how about the electromagnetic radiation? We have X-rays, we have gamma rays, we have radio, optical, putting everything together. The existence of such neutron star is the parameter space is greatly limited. So it cannot be a traditional magnetar. The magnetic fields cannot be very strong. It has to be below, say, 10 to the 12 Gauss. So there might not be a neutron star there. On the other hand, I don't have time to discuss details, but the modeling, the kilonova emission itself actually benefit from adding a long-lasting neutron star with a lower magnetic field there. But all these things are just possibilities. Do we have any smoking gun evidence? So this is something we haven't posted, but this is a paper currently under review led by Luigi Pirro. We found a late-time X-ray flare-like emission from this event at about 150 days after the burst. The significance is not high, below 4 sigma, but what's intriguing is that this flare seems to fall into the right region as the X-ray flares we know of following the traditional gamma ray bursts. Within the delta FOF and delta T over T domain, it is the delta T is very, very short, and the delta over T is very short. So the region, the shaded region is anything you can explain with the external shock. But the red cross is something, this flare, which cannot be explained by any of those models. One requires that the central engine restarts at about 150 days. Another further evidence is that we see this decay slope seems to quite similar to, it's very steep, T2 minus 10, 9, 10. If you try to make the so-called curvature effect work, alpha equals 2 plus beta, I don't get into detail, but you need to shift your time towards the beginning of the flare, which is quite similar to other X-ray flares. So this may point towards a long-lived neutron star or even quark star. So the implications here is that if this is true, then MTOF is large. So previously, if we believe that we form a black hole, then the MTOF, the maximum mass of the non-rotating neutron star, cannot exceed 2.16 to 2.28 solar masses. But now this number becomes a lower limit instead of an upper limit by combining with the gravitational wave data tidal deformability. So we rule out a lot of equation of states, and only some Goldilocks remain. But this thing is consistent with the conclusion drawn from short GRB analysis. For short GRBs, we actually have the evidence suggesting this supermassive long-lasting neutron stars. Okay, so I move on to the second part of this tale of two bursts about fast radio bursts. Vicky gave an excellent review from the observational point of view, and I want to just say that the history is astonishingly repeating itself. Just comparing between these two fields. We can already show this. Again, it's a year ending with 2007. Duncan Lorimer published this famous Lorimer Burst. Of course, this time, the burst itself happened in 2001. But the data just sitting there, not noticed until later, and the paper was published in 2007. But similar to the GRBs, it took even longer, 80 years, to confirm their astrophysical origin. First, it's just one event, and people started. There are other events look like this, but they are apparently not from cosmological radius, and people started to think that these are not real. Until 2013, 4 more bursts were published in the Parkes group, but in 2015, finally, they found that those so-called peritons are related to microwave bursts, and rule out those things, and finally, one can say these are really astrophysical origin. About the observational clues, Vicky gave an excellent review, and she keeps saying that I will discuss the physical origin, but I cannot say much more than what she already said. These are the 4 solid statements one can really make. The first one is because they have millisecond durations, these have to be compact objects. The simple argument is, and just use the size divided by speed of light that will give you the characteristic time scale. A millisecond only point towards the size of the neutrons or a black hole. High latitude, high dispersion measure, that's point towards cosmological distances. And here I listed the luminosity, which is 10 to the 43 ergs per second. Extreme brightness temperature, so this is another way to talk about the luminosity, but this is in the radio community language. But this brightness temperature is almost 10 orders of magnitude higher than the radio pulsars, which have been already super bright in the radio sky. The third statement is high rate. Vicky said it's about 1,000 per day per all sky, which means this has to be a common phenomenon, cannot be very rare. And finally, at least one of them is repeating, so at least that one is non-destructive. So we cannot say that about the other things. However, we can still compare between these two fields, GRB and the FRBs. We are actually going through the same steps. Are the astrophysical took like several years. This is already confirmed. Where are they? For GRBs, it took 30 years to figure out their cosmological distances. And for FRBs, it actually came as a surprise. It came much quickly, but it's mostly because it is repeating. For the non-repeaters, we still take a long step to figure out where they are, because without repetition, it's hard to pin down their locations. And step 3, what make them? For GRBs, in 98, we found an association with the supernova type 1c. And for short GRBs, until last year, 2017, we finally found the association with gravitational waves. But for FRBs, there's a long way to go, because these are intrinsically less energetic, less luminous events, and very hard to find their counterparts. So for now, we cannot say much. But both fields are observationally driven, and there's healthy dialogue between observers and theorists. I think this is another common feature between these two fields. And the history, as I said, is repeating itself. For the GRBs, we had a repeater to begin with, and later it turns out to be something else. And FRBs, we also have a repeaters to begin with. Of course, the simplest explanation is, okay, all the others are repeating, but just that we haven't detected them yet. But we have to keep our minds open that there could be non-repeating ones, intrinsically non-repeating ones. And this was our recent work. We did a little bit more study, just assuming, I don't get into the details, but just assuming that all the other FRBs have similar characteristics in terms of repetition as this repeater, then they should have already been detected. The chance though, of non-detection, none of those have been detected to repeat, is 10 to minus 4 to 10 to minus 3. This is a conservative limit. Okay, the next question is what may make them? Again, it's very similar to the early years of GRB field. This is an incomplete list. But again, the same can be stated. Most of these models should be wrong. I don't have time to go through all these models in detail, but just to pick up something which have my personal preference might be good, but still nobody knows what's going on. So there are two broad groups of models. One is the repeating FRBs. For repeating ones, because the familiar sources are radio pulsars or magnetars. So from the most familiar case, we know that some pulsars, like crab pulsar, is occasionally emitting very, very bright joint pulses. Sometimes it has a nanosecond duration, so-called nanoshots. Putting those to the cosmological distance, see what happens. Even those we cannot see. So one needs to extrapolate those joint pulses to several orders of magnitude higher, arguing that, okay, some of them can produce even stronger nanoshots or joint pulses, and those are the FRBs, and those definitely will repeat. From the magnetar counterparts, the context, magnetars showing flares, bursts. Some of them are called joint flares, and this joint flare, there's a very early short Hawk spike, and one speculation is there might be some short duration radio emission associated with that. And one can also say from different arguments based on the host galaxy of this repeater, which is quite similar to long GRBs or supernovae, then there could be the burst of rapidly rotating millisecond magnetars, and maybe those millisecond magnetars are doing something crazy to produce this FRB. So one possibility is make synchrotron maser something outside the magnetosphere. There are also suggestions that comets are falling onto neutron star. And my personal favorite, of course, because I proposed that, is that we can have a normal neutron star. It may not be a magnetar, but this thing is just sitting somewhere. Normally, no observable effect, but there's a nearby explosion, or it could be an AGN flare, could be a gamma-ray burst, could be a supernova. And when the stream comes to the neutron star, then quickly will reconfigure the magnetosphere of the neutron star and make FRBs. If this combing, I call it cosmic combs, if the combing is marginal, one can make repeating FRBs. So these are the models for the repeating ones, but we should not forget about the catastrophic ones, even though we don't have a direct proof for them yet. One concern is about the event rate. These are very, very common. However, the current observed value is going down by almost 1 order of magnitude compared to the earlier values. So the event rate of the true FRBs and these merger events getting closer. Still not quite enough, but it is possible. Okay, so besides going to mergers, there's one possibility. It's called so-called pulsars. So if we have a supramassive neutron star, which is a neutron star supported by rotation, if it's not rotating, it should be a black hole already. But because it's rotating rapidly, it is still alive. But eventually, when it slows down, it will collapse to make a black hole. In this case, because black hole cannot have hair, the magnetosphere from the closed field line region will be ejected, and that will give rise to a radio burst. So this is called pulsars, proposed by Falca and Razzola. And because we are doing GRBs, especially short GRBs, we see some evidence of supermassive neutron stars. So we said, okay, maybe if this scenario is correct, so at the end of the so-called X-ray plateau of GRBs, okay, we can make FRBs as well. So Then we get to the more exciting ones, even though may not be correct, because at this meeting we discussed a lot of gravitational waves. So neutrons, double neutron star mergers. So there have been two suggestions. Totani said during the merger, if you form a temporally maybe a hypermassive neutron star, there's a reorganization
with the sun, and you would naturally expect these sorts of events to happen. So what are the arguments against that being a mechanism? Is it the energetics or something else?
And it's not my model. My personal preference, because we know radio pulsars are doing this, making high brightness temperature, high luminosity radio bursts, and all these pulsars are doing from inside out. So anything that can make even more luminous radio bursts have to somehow make everything organized and starting from the bottom. So in this regard, I personally don't think gravitational, like a accretion process can make this. But there are arguments around that. Right now, I cannot say that anything is ruled out.
But maybe if I can make a comment, Malrudum, I would say that every time there is something strange, a comet model.
Oh, yes, it will show up, yes.
Okay, so let's thank Ming again. Thank you.